Ladies and gentlemen, boys and girls, welcome to another lesson from Transparent Physics. In this episode, we are going to be continuing our series on energy, work, and power. Specifically, we're going to be continuing our discussion of work in the context of positive work and negative work. And heck, we'll even talk about doing no work at all. Some of us are experts. Real quickly on the administrative side, if any time during this video you're like, hey, that makes a lot of sense, please consider liking the video. If you have any questions about how I explain something, leave something in the comment field below. And to learn more about what's coming next from Transparent Physics and to help the channel grow, please consider clicking the subscribe button, maybe right now. And in this lesson, we're going to be pretty laser focused on talking specifically about how we're going to use the better equation for work, as I introduced in the last episode. And within that context, we'll be discussing in more detail positive and negative work. And the star of this episode is going to be the cosine function. And you know, you can't spell trigonometry without T, so maybe you should brew yourself a cup right now. All right, then a cursory review of the bestest work equation. I encourage you to watch the previous episode for more details. We have the equation work equals FD cosine theta. Both F and D have the vector hats on top of them. That's a reminder that as being entered as a vector quantity in that equation, we want to be both aware of the magnitude of the vector, but also the direction. And the direction comes into play because theta is the angle between the force and displacement vectors. This is different than I often use angles in this series. I often take angles as defined with respect to the positive x-axis. In this case, theta is only and exclusively the angle between these two vectors, even if the one vector is not lined up with the positive x-axis. Let me show you what I mean. So in this case, we have force and displacement both pointing in the same direction. Sometimes I ask students to imagine these are alligator jaws. In these cases, the alligator jaws are closed. There's no angle between them, so the angle is 0 degrees. In another scenario, again, alligator jaws are still closed. The alligator's looking up. You're walking on a bridge above him. He's looking up at you. Even though the vectors are pointing at 90 degrees, the jaws are still closed, which makes the angle still 0 degrees. Next scenario, the alligator is sort of looking up at a bit of an angle, got his mouth open a little bit. We are not interested in the angle of F with respect to sort of some visualized positive x-axis. We are actually interested only in the angle between the force and displacement. So in this case, the angle is 35 degrees, regardless of what specific direction those vectors are oriented in. And then again, I don't know how the alligator would do that, but the idea is that you know, the force and displacement vectors are pretty far spread out. In this case, the angle between them in this case would be 120 degrees. And again, I normally take the smaller of the angles. I guess you could, you know, take the exterior angle instead of the interior angle. I just never do. I always take the interior angle as far as that goes between the F and the D, and that way you'll always end up with an angle between 0 and 180. All right, and students come in introductory physics with lots of different backgrounds in trigonometry, so let's spend a moment talk about cosine. Here's a quick test. If you can draw the cosine function on the back of a napkin right now, you don't need to watch this slide. But if you can't, stick with me for a second. I think it's going to pay off. Remember, trigonometric functions basically take an angle, you put it into a formula, and it gives you a different value back. Cosine is going to give you a set of values like this. Now, when you traditionally draw cosine, you don't stop at 180, you go all the way to 360. But in this context, we only need to go 0 to 180, so I'm going to stop it here. And if we plug a 0 into cosine, you get a positive 1. That's the maximum value cosine can give you, is a positive 1. The angle, as it gets closer to 90, is going to give you a smaller value till you get to 0. And then as you get to 180, you're going to get all the way back up to -1. That's also, you can't get a value that's bigger in magnitude than 1. That's the biggest the cosine can give you. It might give you a positive 1, it might give you a -1, but that's it. It can't get you any bigger than that. And in the first 90 degrees, you're going to get positive values. In the second 90 degrees, you're going to get negative values. So you're looking at this, the magnitude is changing, and also then it's changing from a positive to a negative. in a very sort of classic trigonometric curve here. If we are in the first 90 degrees, this gives us a positive value for the cosine, which is going to give us a positive work from the equation. The only time we're going to get a positive or a negative out of the equation is from the cosine of the theta. Both force and displacement themselves are just as magnitudes. So if you're ever going to get a negative sign, you'll get it from the trigonometric identity, not the force or the displacement. And if we're looking at 0 degrees, again, 0 degrees, we go with the crocodile metaphor. The crocodile jaws are closed. Doesn't matter what orientation the crocodile is pointing her head. The angle between them is 0 degrees. So you get your maximum value there. If we imagine the crocodile's jaws are open slightly, we are still going to be in the positive work zone, even if this isn't lined up perfectly with 0 degrees. We can say the angle between the crocodile jaws here maybe is 30 degrees. And 30 degrees gives us still a pretty healthy value for the cosine of 30 degrees, so that the value of the cosine of 30 degrees would be 0.8-ish something, I would say. And again, that continues. Now it drops off a little faster as you get to 90. I couldn't find a picture of the jaws open at 90, but if I could, that would be a 0 cosine scenario. And well, the cosine of 90 would give you a 0. That would be a no work scenario. We're going to talk about that. And then finally, if the jaws open wider than 90 degrees, say like this, we're going to be in the negative work scenario. And we'll talk more about what positive work and negative work mean in this context. Right now, just focus on the idea that it's going to give us a negative value. So this could be the displacement, this could be the force. It's wider than 90 degrees. Maybe this is 120 degrees or something. So if we plug 120 degrees into the cosine function, it's going to give us a value of negative 0.5-ish or so. And again, this becomes very important in applying the work equation. Depending on the angle between the force and displacement, you can get a positive or a negative answer, or even no answer. And that's what we're going to focus on over the next couple slides. Okay, then just try to keep that picture of cosine in mind as we move forward with discussions of work. In the last lesson, we introduced the idea that work is the transfer of energy through motion. So transfer can be adding energy to an object or taking energy away. So positive work adds energy to an object. And this occurs when the cosine of the angle between force and displacement gives us a positive value. As the graphics showed us just a moment ago, that occurs when the angle is equal to 0 through less than 90. And the closer it is to 0, the larger that value is going to be. And in this case, force is going to add energy to the object. And so, for example, in this picture, Loki is pushing the girl. The girl starts at rest. He exerts a force on her, pushing her to the right. She moves to the right. She moves in the same direction as his force. So she picks up kinetic energy from his push. And the smaller the angle is, the higher the energy transfer. In this case, the force and displacement are exactly in the same direction, so very small angle. Which means a high rate of energy transfer there. Other examples might be, say, pushing a wagon from behind, or a lawnmower or anything like that. If you're pushing it in the direction that it's moving, you're going to give more oomph than, say, if you're pushing up or pushing down at an angle. Now, this doesn't just have to be kinetic energy as well. You can change the potential energy. If you move an object upwards, you can increase its gravitational potential energy. The displacement is up, the force is up. So even if the object isn't necessarily speeding up, it is increasing its gravitational potential energy. Well, all right, then it wouldn't be very fair if there was a way to add energy to an object without being a way to take energy away as well. And this is negative work. Negative work occurs when the cosine of the angle between force and displacement gives us a negative value. You can remember we saw that in the graph when it was between, well, it had to be more than 90 degrees because 90 degrees is 0. A little bit above 90 gets us a very, very, very small negative value. And then that value gets larger and larger as we get closer to 180. And at 180, it is a full -1. So that's the maximum negative value that you can get. And this force takes energy away from the object. Now, the closer you get to 180 degrees, the higher the energy transfer is. So to get your maximum removal of energy, what you want to do is have your force acting directly opposite of the displacement. So in this case, if we look at the red puffball creature there, the red puffball creature is moving to the left, but it has a force acting to the right, acting on it by the orange puffball, and that removes energy from the red puffball creature. Other examples might be friction causing an object to come to rest. This is sort of a classic one. Again, friction does not always bring an object to rest. You should check out the lessons on transparent physics about friction. But if an object is, say, sliding across a table, if it's sliding to the right, friction acts to the left, and friction does remove energy from the object. But that's not all friction can do. Another maybe more complicated example would be the idea is if we have a bucket and we're lowering the bucket. If you have a rope attached to the bucket, you are actually pulling up on the rope. So your force is acting up, but the bucket is going down. And if you allow the bucket to descend, say down a well, while pulling up on the rope, that bucket is actually losing energy. Now, it doesn't have to lose kinetic energy. It can lose potential energy as well. Any energy qualifies for work here. So the idea is that it could end with a lower potential energy as the result of you doing negative work on it. So lots of circumstances where this can sort of come into play. All right, then to wrap up this discussion of positive work and negative work, we should probably explore the no man's land where no work is being done at all. In the equation W equals FD cosine theta, we can seek scenarios when there is no change in the object's energy. And that occurs when any one of these three values is equal to 0. When the force is equal to 0, when the displacement is equal to 0, or when the cosine of theta is equal to 0. So let's go through each of those one by one. Obviously, if you don't apply a force, you're not going to change the energy of the object. If no force is applied to an object, its energy will not change. And that's the way life works. So you need a force to start with. Next up, if there's no displacement and you can apply a force, but if the object doesn't move anywhere as a result of that force, if the displacement is 0, you're not changing the energy of the object. A great example of this would be, say, if you're standing there helping somebody move and they hand you a really heavy box of textbooks, and they say, just hang up for a second, let me get something else. So you're standing there for 30 seconds holding this like 50-pound box of textbooks. The energy of that textbook, the box, is not changing, even though you might be exerting a lot of effort. So effort does not translate to work. The only way that you get work is if the energy is actually changing. So another example of this might be pushing against a brick wall. You can spend all day pushing against a brick wall. You can tire yourself out sufficiently doing that, but that's not going to change the energy of the brick wall, so you're not doing any work. So holding an object at rest means no displacement. And then finally, the last one is when force is perpendicular to the displacement. When force is perpendicular to the displacement, as we talked about when we looked at the cosine graphic a couple slides ago, the cosine of 90, or again 270, any 90-degree iteration of that that's not opposite each other, that value is going to get you, cosine of 90 is going to get you a value of 0. Now this one is maybe the least intuitive to think about, but an example of this would be, say, carrying a tray of food. Again, the ultimate question we want to ask ourselves is, is the energy of the object changing? So if the object here in question is a tray of, I don't know, desserts or something, it looks like maybe. So the gentleman in the blue sports jacket is exerting a force up on that tray. So he's pushing up, the tray is moving to the left. So his force and his displacement are at 90 degrees. So he is exerting a force on the object, but it is not increasing in his energy as he's following the young girl. I think this is one of those Master Chef shows. The energy of the desserts on the tray aren't changing. Now they start with a certain amount of energy because the tray is moving, but he's not speeding it up. He's not raising it. He's not lowering it. So by the time he gets done walking down the room here, the object does not end up with more energy. So you can exert a force on an object. It can move, but it's possible that you're not contributing to any change in the energy in that process. Again, probably the least intuitive one of it, but when any of these three is equal to 0, you've identified a circumstance where there might be no work being done. All right, and just like back when we talked about forces, you didn't really know what was happening to the object until you looked at all the forces acting on the object. The same applies to work. You don't really know what's going on until you look at all the work being done on an object. So let's take a quick example of this. No numbers, just conceptually, and recognizing that the sum of all the work being done on the object is the net work, and that's going to tell you about energy change. So real briefly, we're back to our couch again. We're pushing it to the right. You push it to the right. The force is to the right. The displacement is to the right. That means you're doing positive work with your push. You're adding energy to the object, potentially speeding it up, but you've got friction acting in the opposite direction. So displacement's to the right, friction's to the left. That angle is 180 degrees. So already you have two forces that are sort of battling each other. The push is adding energy to the couch. Friction is taking energy away from the couch. You can see by the fact that I drew the blue arrow longer than the orange arrow, the push arrow is longer than the friction arrow. That means that push is actually winning. It's an unbalanced force. So the couch is going to be speeding up, but it wouldn't be speeding up as much as it would have been if it wasn't for the fact that friction was pulling some energy out of the system. Again, it's very similar in application to looking at it in terms of unbalanced forces. And as it well should be, because the physics doesn't change. We're just looking at it from a different perspective. In terms of gravity and the surface force, aka the normal force, yeah, the floor is pushing up on the couch. Is that changing the energy of the couch? No. Gravity's pulling down on the couch. Is that changing the energy of the couch? No. So in both of those circumstances, the angle between the force and the displacement is 90 degrees. And it doesn't matter whether the force is pushing up like it is for the surface force, the normal force, or if the force is pulling down like it is for gravity. The angle between the force and the displacement in both circumstances is 90 degrees. And that means that no work is being done. So in a real problem, we would have numbers, measurements associated with all these values, and we could end up calculating the total energy change of the couch. And we might just do that in the next lesson. All right, then, quick summary. Remember, work is the transfer of energy through motion. So you can add energy, positive work. You can take energy away, negative work. And how do you know whether you're adding energy or taking energy away? It's through theta. It's the angle between the force and the displacement. Don't take it with respect to the positive x-axis. It might be moving along the positive x-axis, but that's just a happy coincidence. That doesn't mean that you always measure with respect to the positive x-axis. My recommendation is always to draw a sketch of the displacement vector, draw a sketch of the force vector, have those vectors starting at the same point, going out from some central dot, and then you can use that to determine what theta would be. And next lesson, we're going to do a practice problem to show you how all this works. And as always, thanks for watching. Hopefully my discussion of positive, negative, and no work has made the scenario a little clearer for you on this lesson from Transparent Physics.